Hello everyone, my name is Yukun. Today I'm going to present our work revisiting the evaluation of uncertainty estimation and its application to explore model complexity uncertainty trade-off. In this talk, I will first introduce what is uncertainty estimation on neural networks. Then I will talk about the two popular use cases of uncertainty estimation, selective prediction and confidence calibration. For each of them, I will discuss the problem in the evaluation method and how to address them. Finally, as an application and validation of the proposed solutions, we will explore how the model complexity may affect the uncertainty estimation quality. Let's first be clear about the problem setting. The uncertainty estimation we are talking is that for each input xi from the data distribution, the model will output a prediction y hat I and the confidence score ii. So why we need this uncertainty estimation? The reason is the real-world problems are so diverse, and it is so difficult to train a model to achieve 100% accuracy or be capable to deal with any scenarios. So the confidence score will help us to identify and deal with the potential failure properly. Finally, why we want to focus on the evaluation of uncertainty estimation quality? The reason is this problem is particularly challenging because in many cases, the ground truths of uncertainty estimation are not available. So let's first see selective prediction. If you see the figure on the top, without uncertainty estimation, we will have deep neural networks to process the input and get the output. And because the model is not doing perfect, all the tasks can be too critical that we cannot afford any mistakes. So we will have human experts to inspect the predictions and make corrections if necessary. So in the second row of this figure, you can see that with uncertainty estimation, we still have the model to process the input and get the output. However, the predictions will be separated into two subsets. The left is the high confidence subset and the right is the low confidence subset. And the high confidence prediction will be committed directly, but the low confidence prediction will be inspected by a human and doing correction if necessary. So in this case, the human will only need to inspect a small subset of the prediction and the cost is greatly reduced. So in this case, the confidence score is used to distinguish the correct prediction and the wrong predictions. This is a standard binary classification problem. So the standard evaluation method for the uncertainty estimation in this case is the AORC and AOPR, which is kind of the conventional metrics. So now let's see what's the potential problems of this evaluation metrics. The key point here is the comparison of AOPR or AORC is meaningless when the prediction models are different. This happens in many cases. For example, when you are doing uncertainty-aware training, or the model architecture changes because you want to do good uncertainty estimation, or the accuracy can sometimes be improved as a byproduct when you use ensemble or Monte Carlo dropout for uncertainty estimation. In this case, the comparison is meaningless because the prediction model determines which samples, which predictions are correct and which predictions are wrong. And different prediction models means different binary classification problem. So with different problem, it is meaningless to compare the AORC and AOPR. Our solution for this is to use a new matrix called area on the risk coverage curve. The coverage is defined as a proportion of the high confidence predictions in all predictions. And the risk is defined as a performance measure of the high confidence prediction. We have proved a consistency among AURC, AUPR, and AURC. In the case that the prediction model are the same, so they are all reliable metrics in this case. In contrast, the AURC is also reliable when the prediction models are not the same. In this case, the comparison of AUPR or AURC is meaningless, but the comparison of AURC directly measures the overall selective prediction performance. The AURC is also better in generalization. For example, in image segmentation, the pixel-wise evaluation of AUPR or AURC is not useful, but the AURC can put the dice coefficient of Jacquard index, this kind of segmentation quality metric, into the definition of risk. Thus, we can still use the AURC to measure the performance. So now let's see another popular use case of uncertainty estimation, confidence calibration. In this case, we expect that the confidence score approximates the probability of the prediction being correct. So if you see this equation, the R is our confidence score, B is the scalar value between 0 and 1, and S is the correctness score, which means S is 1 if the prediction is correct, and S is 0 if the prediction is not correct. So the standard matrix is expected calibration error. However, in this equation, we do not have the expectation, so we have to estimate them from the limited number of samples. The standard practice is to divide all samples into 10 uniformly distributed bins based on their confidence score. So, as you can see in the figure below, then after dividing the samples into these bins, for every bin, we will calculate the average accuracy and the average confidence in each bin. Then their difference becomes the calibration error of this bin. So in this way, we can calculate the maximum, we can calculate the expected calibration error, ECE, and also the MCE, the maximum calibration error, is clear because it's simply the maximum of the calibration error in the 10 bins. So the problem of this evaluation method is that it highly depends on the bin. How you define the bins will affect the numbers you calculated, and the neural networks usually has the highly non-uniform confidence distribution, as you can see in the figure on the right. The samples are concentrated in the high confidence area, and therefore the uniform distributed bins are not suitable in this case and lead to a number of problems. These problems are discussed in the paper, but I will skip this because of the time limit. So in general, our solution for this problem is to using an adaptive bin. The new method makes the bin distribution dependent and achieve a dynamic trade-off between the number of samples and the range of the bin. The figure below are some examples of using adaptive bin. Now we have finished the discussion with the evaluation metrics. Let's see how can we validate and utilize them. We all know that the model complexity and accuracy trade-off is well explored. For a certain model architecture and training algorithm, there is a smooth curve of accuracy versus complexity, as shown in the right figure. And our understanding on such trade-off is crucial for the system designer to find a sweet spot, but this understanding only exists for the accuracy, not for the uncertainty estimation. Therefore, we use the new metrics to do such exploration of complexity uncertainty trade-off to see whether the uncertainty estimation quality has a similar trend with increasing model size and model complexity. So here we show some results with the wide rest net and the dense net on CIFAR 10 and CIFAR 100. In the figure on the top left, we see that with increasing model size, it is increasingly difficult to identify wrong predictions. However, if you see the figure on the top right, the overall selective prediction performance is actually increasing. This is because the selective prediction depends on both prediction accuracy and the uncertainty estimation quality, and it benefits from the higher accuracy of bigger model. In the bottom row of the figure, we see that the calibration error actually does not has a strong, consistent trend with model complexity. However, using adaptive bins, we can get a much stable maximum calibration error estimation. So finally, here are some takeaway messages. First, the evaluation of uncertainty estimation quality is not trivial. We need to choose the metrics carefully. Second, when changing the model complexity, the uncertainty estimation quality can have a very different trend with the one of the accuracy. That's all. Thanks for listening.